So today I want to talk about an idea I have for a more efficient cooling device, and I want to go a little bit over heat engines. So what is a heat engine? Well, a heat engine is something that uses heat and a difference in heat to drive an engine to make electricity, to make mechanical power, and there's many types. It can be a car engine, it can be a stirling engine, it can be a gas turbine, and one of the most efficient theoretically is a stirling engine. Now all heat engines rely not on heat exactly, but the difference in heat from hot to cold. Theoretically, the most efficient they are is T8 minus TC divided by T8, where T8 is the highest temperature and TC is the coldest temperature. And that is because you have the heat pushing against the cold, but the cold pushes back as you compress it. So you minus them, then you divide by T8, which is the total theoretical energy. Most heat engines, they'll only run about 20 or 30% the efficiency of a full, of the theoretical maximum efficiency, which is called the Carnot cycle efficiency. One of the few exceptions that really operates in upper bounds is called a stirling engine. Now there's many different types. There's an alpha, beta, gamma types and a couple other ones. And Wikipedia has a whole nice page on it that I checked is pretty accurate. I mean, as far as I'm concerned, it's 100% accurate. And what the stirling engine does is instead of having, it has a couple innovations. Instead of having one piston, it has one piston that just goes in the same cycle. It has two pistons that turn the thing, or more, that are each out of phase, meaning they don't go up and down the same rate as you see in these pictures. Now this is done in such a way that when one is squeezing, you're squeezing a compound that gives off heat, and you use that heat to heat up the other piston so it goes up more. And then that cools down that piston that you're squeezing stuff so it can get colder and squeeze more. So you're cooling down one piston and heating it up. You exchange energy. You can see that in these diagrams nicely that they have on Wikipedia, where here it's squeezing, here it gets hotter, but heat then gets absorbed by the thing that's expanding. Another innovation is that you have little things that help, called the Regenerator in it. The Regenerator takes away some of the heat from the hot side, stores some of the heat from the hot side for the next cycle to make it a little more efficient. Now that's all good, and so, but stirling engines have a lot of problems. They are the most efficient, but they do not work well if they require sometimes heavier, sometimes less heavy items, but they can't, because they're so not in this perfect cycle, they can't really speed up or slow down very fast. And they're made to operate best at more of a singular speed. And that's one of the major disadvantages of them. Then they also can be heavier and dependent on design. So even though they're more efficient than like a gas engine, a car built on it could never accelerate fast or stop fast. Have to repeat it, or it would get this nice cycle that's going through with the heat exchange would get disrupted. Another thing is that some stirling engines have, compared to turbines, not compared to like a gas engine, have more moving parts that you have to precisely fit, that there might be friction, which might be energy loss, and so on and so on. But we're fixing those slowly. And they might be more for stationary things like solar power or something, where the heat up and cool down is a lot slower, so it doesn't matter as much. It's readjusting. So anyways, what happens when you run a heat engine in reverse? Well, you can have two things. Either you can heat up something or you can cool it down. If you compress a fluid and take away its heat because it gets hotter, You can use that to heat up a house. But then when you expand it, it cools down, and you can use that cooler thing to absorb heat from a house, then heat up on the outside, and it releases that heat. When you squeeze it, then it cools down again, and you go one way or another way. Either you take the heat from the outside and pump it inside, sort of, or pump the heat from inside and outside. The more efficient the heat engine is, in one way, theoretically, the more efficient it will run in reverse when you're using it to cool up or heat up a place, instead of making it in mechanical electrical energy, theoretically. The problem with this is that stirling engine is that for a lot of fluids in it, they don't absorb heat well enough to really cool down a place fast or efficiently, and that's a major problem. Now, I have a proposed solution to this using something called a vortex tube, and I will explain that in just a second. But here is a picture of a vortex tube, again from Wikipedia. So in the vortex tube, we take some air and we make it go really fast down, and it spins up, spins here. And by the way, most refrigerators and heat pumps are the opposite of refrigerators, that they pump in heat, but they both use like the reverse of heat engine, use a phase changing material, which means they go from liquid to gas or vice versa, which is not theoretically the most efficient, but gas to liquid absorbs a lot of heat. Gas to gas compression will be more efficient, but it doesn't absorb nearly enough heat to make it practical or give off enough heat. So this is a way around that we could use a stirling engine with just gas, which will be more efficient. And when a stirling engine would usually just operates on gas, not phase changing material. So here the gas or fluid enters, and then I do a trick. Then it does a trick that this whole section here is actually a big cylinder. So it enters from the side. Kind of imagine it as a Coke can or a cylinder with near the side is a little straw or something attached to it, and air goes in there, spins around the side because it comes in the side and spins a little bit around. It's deflected, and it has this vortex that spins all the way out, but then it hits this blockage. Some of the air compresses and comes out here hotter, but some of it gets deflected and goes out here and comes out of this expanding nozzle in the reverse direction. Now the outer air is hotter because it gets compressed here, and that compression heats up the gas. The inner gas here is colder because it's expanding and gets less. Now, also you have this cyclone effect to separate out the air, where hot air is less dense and spins faster out. Can spin faster, where cold air gets more compact and kind of settles in the middle. So you also have the spinning effect, kind of separating it out by density. Usually something that's more dense would spin on the outside, but in this case it's also a pressure gradient that forces the hotter things spread out more from the center. How would maybe a better explanation would be the faster stuff moves away from the center more than this cold stuff that takes longer with the molecules. So you have this effect. But imagine instead here you put the piston. Now the piston, when it goes down, forces some air to spin, and then the hottest part comes here, where I put the heat exchanger. Now because the hottest air is on the outside, it can give off heat a lot more fast because it's hotter. And then it keeps the hotter gas keeps coming here because it's separated. Then the cold gas coming out here can absorb more heat. Now, when I need to reverse it, I just pull out air. Then for a while, the cyclone decreases in efficiency because it stops. It spins one way, then it's pulling in the other way. But eventually it's going to spin the other way, and that's going to actually cause the cycle to happen over again. So it's constantly, this side is hotter, and this side is constantly spewing colder gas. How would I, and yes, there's this brief in between where this system is messed up. Now if I put a heat exchanger here, I can get heat off very much, and here I put the heat absorber. Just put this piston up and down. Then if I put two pistons next to each other, like this system but separated out, I actually have a stirling engine that can be run reversed as either a heat pump or a heat cooler. I'm trying to find a two piston one. Here is, there's not enough. There's two piston ones, but there's two piston ones where they are different types. Another thing I could do to make it even more efficient and keep it spinning in the same direction is I could have a crossbar here where actually, so imagine that I have actually two openings here, and this I'll draw on the sketch pad. Hopefully, I was hoping it didn't save everything, but it did. Instead of having this vortex tube where two things are totally different, I can have two stirling engines connected to the same vortex tube in a one-way valve. So, Apple A. Let's see if it lets me copy. So instead, I could have the whole system set up, and I will just briefly try it. This is the ugly drawing of the year award, and it's acting very slow for some reason. But anyways, I have it like this with another pump here, and here I have the exit. So the same idea with spinning, but here I pump it so it pumps in air like this, and it spins around, spins around. Then here I have it suck in air over this piston, which I will draw in a second. Now when I reverse it, instead I have a one-way valve that cuts it off here, and a one-way valve that cuts it off here, and instead it will just pump it over to here with one-way valves, and that way the cycle is always continuous in the same direction. And then this air duct is connected. This hot air that's cooled down is connected somehow back into it feeds in to one of these stages, or this feeds into one of these stages. And actually with the feedback loops, we don't even need this connection here, so I can erase that. But that will make it even more efficient, where we can have the two pistons driving continuous motion and really separate out. The exact lengths and everything here, a ton of fine tuning. But it's an idea, and I think it's worthwhile. Well, thank you very much for listening. I hope you found this interesting. Please like and subscribe. It really helps the channel out. Thank you very much. Goodbye. And also, I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really hard.